Hey guys, welcome back. And today we're gonna be doing orbitals. I apologize for the background sound, but I'm trying out a new software and my headphones aren't working for some reason. Okay. Anyways, let's go through this. We have a lot to get through. So first we're gonna look at principal quantum number, and you should remember that the principal quantum number just means the shell number. So let's say you have carbon, which has 7 electrons. So it has 2 in the middle or the start, and it has 5 on the outside. So we have it like that. So the principal quantum number of the first shell is n equals 1, and the principal quantum number of the second shell is n equals 2. And so the principal quantum number is used to write the electron configuration. So for example, the electron configuration of carbon, you should remember, is 1s2, 2s5, because, oh, actually, sorry, carbon is actually 6 electrons, I believe. That was my mistake. It has 6 electrons, not 7. I was thinking of nitrogen there. So it has 6 electrons, so it's 1s2 and 2s4. And the s's, remember, they mean the subshells. So each shell has subshells. So the first shell has only s, the second shell has s and p, the third shell has spd, and the fourth shell has spdf, and so on. And so remember, in each subshell there's a defined number of orbitals, and orbitals are drawn as a square. So for S, let's draw a table down here. For S here, let's draw a table. For S, we have the number of orbitals, and we have number of electrons. So the number of orbitals in S is just 1. You just need to know this. And for each orbital, it can hold 2 electrons. So the number of electrons that S can hold is 2. And let's keep going. Let's go to SP now. So P has now plus 2 orbitals. So it has 3 orbitals now. So it has 3 orbitals. And so you just multiply by 2 to get the number of electrons. So it's 6, like we did here, multiply by 2. And for D, you can guess it. It's just 2 more, plus 2, and then down again, plus 2, so we get 5. And we multiply this by 2 to get 10. And for F, you can do the same thing. It's 7, and you multiply by 2, and you get 14. And so that's how the electron configuration system works, because we say 1s2 to indicate that it's the first shell, the s suborbital, and there's 2 electrons in the s suborbital. And for example, if you had 1s2, 2s2, 2p6, 3s1, that would mean that there's 2 electrons in the 1s subshell, there's 2 electrons in the 2s subshell, there's 6 electrons in the 2p subshell, and there's 1 electron in the 3s subshell. And that's how our naming works. And yeah, that's pretty much it. And so next we're gonna do the 3 rules. These are very, very, very important rules. And these come up when we try to draw the energy diagrams. So when we have when we have a subshell, for example, let's say we want to see the D subshell. So we have 5 orbitals. So we draw it as a large rectangle with 5 divisions. So we have 5 divisions here. And so basically, let's say we have 7 electrons to distribute between these. So the very first rule here, Aufbau's principle, that just states that the shells are filled based on order, energy level. So if we have energy axes here going up and this is energy. So the bottom shells would be filled first because those are the shells with the least energy, and that would mean that the orbitals with lower energy, like 1s2, 2s2, and so on, those will be filled first. So this will be, let's say this is 2s2, this is 1, or sorry, 2p2, 2p. This is, let's call this 1s, and so let's say this is like 3D, for example. And so the 1s will be filled first, and I'll explain the filling order in these later. And the 2p will be filled next because it's next in order, and 3D is filled next, assuming we don't have anything in between. We do have something in between, but in this particular case I'm just ignoring those. And then the 7 electrons, what Hund's rule says is, the Hund's rule says that electrons should always be in filled in order of the orbitals. So it should always be like this first. So each orbital should have one unpaired electron first before doubling it up to 2 paired electrons. And so we have 5 unpaired electrons, and we need 7. So we just add 2 more at these ones. And the reason why we draw up and down arrows for 2 of the electrons is because if you think about an orbital, and let's say you have 2 up-spinning electrons, if you remember, electric and magnetic fields are caused when charges move or rotate. So when electrons are rotating, they produce a magnetic field, and if they're both spinning in the same direction, the magnetic field gets bigger and bigger and bigger, and it gets very unstable, and we don't want that. So what Pauli said is basically they have to be opposite spin. So one of the magnetic fields goes this way, and then one of the magnetic fields goes that way, and they all cancel out. So there's basically no magnetic field. And that's why we draw them in that crisscrossing pattern where it's up, down, up, down, up, down, and so on. And so yeah, those are the 3 rules, and I just explained the energy diagrams where the lowest energies get filled first. And so yeah, now we move on to sigma and pi bonds. And the first part is something you need to memorize. So for every single bond, let's say we have C and C, this will have 1 sigma bond. And for every double bond, C double C would be 1 sigma bond and 1 pi bond. Remember, these you just need to memorize off the top of your head. You can say, I'll give you a trick later. So it's 1, for a triple bond, it's 1 sigma bond and 2 pi bonds. So now a trick to remember this is that all bonds only have 1 sigma bonds, or 1 sigma bond, and the rest of the bonds have to come from pi bonds. And that's how you can remember those easily. And let's see, if you remember from class, sigma and pi bonds, how do they form? So sigma bonds are when 2 orbitals, let's say we have a p orbital here, overlapping with the s orbital. Oh, I forgot to show you the shapes of orbitals. Okay, so remember, for the shape of an s orbital is just a sphere. You can see that S just stands for sphere. It's not very complicated. We draw an axis here, and it's just, we draw it as a circle, but it's technically a sphere. And for p orbitals, it's like this. Let me show you. So we have one oriented this way, and we have one oriented this way, and we have one oriented this way. So there's 3 orbitals like we showed before when we had p is 3 orbitals and 6 electrons. And so now we have to label these. So this one was just the s orbital. But if we label these axes x, y, and let's say there's an axis like this that goes like this, and that's z. So the one that's aligned with the x-axis, this one here that I'm highlighting, it's p subscript x, and the one aligned with y that I'm highlighting here is py. And actually, let me try to do these in color. So that one is py. So that one is py. Let me just erase this. So that's py. Px is the one aligned with x, and the purple color with, or is this even purple? Is like orange. Wait, what did I just say? Rainbow. Pz, and that will be pz. And so yeah, that's how the orbitals of p work, and those are the shapes. They look like dumbbells, kind of. You can remember it that way. And so when they combine like this, when these two combine using a sigma bond, they form what's called a hybridized orbital, and it's just a combined version of them head on. So it's like a bigger version. And this is a P, and this is an S, and these form a sigma bond. And this is the hybridized version. Hybrid orbital. And so that's how sigma bonds are formed. And you should remember that pi bonds are formed laterally. So if you have a p orbital and you have another p orbital, these two combine using a pi bond, and these become what's known as a hybridized p orbital. Let me draw this. And let's do that, and let's do that, and let's do that. Okay, so this is the hybridized version, hybrid orbital. And so what actually happens is, let me explain it like this. So let's say we have an energy diagram for carbon, and we're looking at ethene. So let me just label these energy. Okay, so let's say we're looking at ethane. Ethane, remember, is an alkane, so it only has single bonds. So it has C and C, and the C's all have hydrogens attached to them. Let me just quickly write those. Okay, so the C, you can see, has 4 single bonds, and 4 single bonds means 4 sigma bonds. If you remember from up here, a single bond equals 1 single bond, sigma bond. Kind of a tongue twister there. And so if you need 4 sigma bonds, remember the electron configuration of carbon is 1s2, 2s2, and 2p2. Actually, I think I made a mistake up here. Oh no, this is completely wrong. S cannot hold more than 2, so it's 2s2 and 2p2. That was my mistake, sorry about that. And so this one, 1s2, 2s2, 2p2, we can represent in an energy diagram. So over here, so we have 1s2, which remember we draw like that, alternating, and we have 2s2. So let me just label these, 1s2, 2s2, and we have also 2p2, but this one has 3 orbitals. So we have 1 here and 1 here. So now sigma bonds are formed by hybridized orbitals. So we have 4 electrons here. We have 4 electrons in the 2 shell. The principal quantum number of 2 has 4 electrons. So you have 2 up here and 2 here. So what they actually do is these 2 combine and they make a hybridized sp3. So because this is 2p, 2p2 in this case, it has 3 orbitals, right? So it has 3 orbitals. 3, and this one only has 1. So what we call them when they combine is S1 technically, P3. So S1 is just S, so we call it sp3 hybrid. And that's how the naming works. So when they combine, you get four orbitals now. Let me just draw these so I have space. And let me just draw. So 4. So this orbital comes in, and these 3 orbitals come in, and they form 4 orbitals this time. And all the electrons get equally separated between them. So it has 4 like this, and like that. These 2 break apart, and one of them goes over here, and they all become single unpaired electrons. And this enables the carbon to form 4 sigma bonds, which are 1, 2, 3, and 4 here. So 4 sigma bonds here corresponds to 4 hybridized orbitals. And that's how single bonds work. And now let's see how double bonds work. So double bonds, let's say we're looking at ethene now. Remember the bond angles, this is 120 degrees. If you can remember why that is, then that's good. If you can remember the name of it, name of the structure is trigonal planar. Just a quick recap on the topic. And okay, let's see. Let's draw the energy diagram again. And energy. Okay, so we have 1s2 as always. 1s2. We have 2s2, 2s2, and we also have we have 2p2. Let's see, okay, 2p2. So now what you need to know is that there's one sigma bond here. So there's one sigma bond, and there's one pi bond here, so pi bond. And pi bonds are made by unhybridized orbitals, so they don't have to be hybridized. So remember from before, the hybridized is when they combine to make like many orbitals, like all of the orbitals combine. But in this case, you only need 3, right? Because you only have 3 sigma bonds. So if you add them up, you get 3 sigma bonds and 1 pi bond. So we need three hybridized orbitals, and 3 hybridized orbitals come from this one and this one here. So these 2 and this orbital combine. So they go like this, and they combine to make 3 orbitals this time, not 4. And they split up their electrons equally. So as usual, these 2 break up, and this one goes over here, and they form unpaired electrons. And this enables the carbon to form 3 sigma bonds. So the 3 sigma bonds corresponds to sp2 hybridized now. Remember, the naming system is different because we only have 2p orbitals that hybridize. And what do we do with this unhybridized p orbital this time? What we use that for is the pi bond, of course. And how this looks in space. Let me draw that real quick. So let's say you want to draw this looking fancy and visual as you can, you know. So you have C, you have the, okay, let's draw the C as just a particle or a nucleus, and let's say it has, how can I do this? Okay, so let's say it has, okay, oh god, my drawing is so bad. Okay. Okay, it's fine. Okay, so it needs to form 3 sigma bonds. So where does it get the 3 sigma bonds from? Let me just redraw this real quick. So it has to hybridize two p orbitals. So what happens is the hydrogens use their s orbital to hybridize with this p orbital. So that one hybridizes. So this one hybridizes together and forms a big one. So let me redraw that. So this one forms a very big hybrid orbital. And next, actually, let me not do that. Let me try this way. So this one combines over here. So this is coming from the hydrogen. So this is s orbital. Actually, that's kind of weird. Let me put this here. So that one combines, and let's say this one also combines. So let's see, this one combines from the carbon. So remember the carbon up here, this one has a sigma bond with the other carbon. So it comes from the S, from the carbon. Just put that there. And so we still have this orbital unpaired, right? So we want to get it paired. And how we do that is, so we have the particle again, or the nucleus. We have the upward facing p orbital, and we have the carbon from the other the other side of the ethene, and these two combine laterally because, as we said, pi bonds are lateral combinations of orbitals, and these form the hybrid orbital I was talking about before over here. Where did I draw it? Here, this shape right here. They combine together and they form that shape. And let me just redraw it over here. These two combine to make this shape. Like that. And so that's what the pi bond really is. And if I just draw in the other two bonds real quick, we have that sigma bond and that sigma bond, one from hydrogen and one from carbon. And the same thing is on the other side, but we're not looking at that right now, but I'm going to draw it anyways. And so yeah, that's how double bonds work. And the key thing you really need to remember is sigma bonds are formed from hybrid orbitals. Hybrid. The two orbitals up here combine with 2s orbital down here, or 2s orbital, and they combine to make three hybrid orbitals, and left behind the one orbital over there to make a pi bond. And last but not least, we're going to look at a triple bond, and we actually haven't come across this in class, but this is called ethyne. That's a cool name, isn't it? Ethyne. Sounds very nice. And so let's look at that. So you guys can try this yourself if you want, if you're brave enough, but let's see. So we have 1s2 as usual, 1s2, we have 2s2 as usual again, s2, and we have 2p2 again, of course, carbon, and we have 2p2. Okay, so we want three bonds now, a triple bond. So we have one sigma bond. Actually, remember, go up here, go back up here, go back up here. So triple bond is one sigma bond and two pi bonds. So what we have here is one sigma bond. So we have a sigma bond here and a sigma bond here from the hydrogen, and we have two pi bonds. So two pi bonds. So we have two sigma bonds and two pi bonds. And remember, what did I say before? Sigma bonds are from hybrid. So sigma bonds are from hybrid. So this one combines with this one to make two hybrid orbitals. They make two hybrid orbitals, and they split up their electrons, and this enables the carbon to form the two sigma bonds that we needed. And the remaining two here, what they do is, obviously, they form pi bonds that the carbon needs. And what happens there is the following. So I'm gonna ignore the sigma bonds and draw it in maybe later, but let's see. So we have this, and we have, let's say we have the z-axis like that, and we have another carbon, and we have this, and we have that. And so both of these are gonna laterally combine. Remember, that's the definition of a pi bond, the lateral combination of orbitals. And they're going to form hybrid orbitals where it looks a little bit complicated. I hope I can draw this. So it goes like this, it goes like this, it goes like this, and it goes like this. And for the side one, it's a little bit more complicated, but should be fine. Like that, like that, and like that, and like that. If you guys can visualize that, it's kind of 90 degrees to the first plane from here to here. And yeah, that's pretty much it. That's how the lateral combinations work. And let me just draw in the final sigma bond. Actually, let me explain how the sigma bonds work. So the sigma bond between the carbons, they use the p orbitals. So they use p orbitals here, and these two combine head-on as a sigma bond, and they form a weird-looking shape, but it's something like this. That was kind of bad. Try again. Okay, that's better. So you have a big region here and small itty bitty regions back there. So we have small regions here and a big region here, and a small region here and a big region back there. So that's how it works. I hope you can see it properly, but if you can't, you can try drawing it yourself. It might give you a better understanding, to be honest. And so yeah, that's basically it. Did I have anything else in mind? I don't think so. Yep, that's pretty much it. And if there is one more example that you guys can try on your own, and that is how the triple bond for nitrogen molecules work. And this is really interesting because it has one sigma bond and two pi bonds, and you can try drawing the energy diagrams if you want, and it's really interesting. So thank you for watching, and I hope you'll stick around for the next video that might come in a few days. So thank you for watching.